take a look at this function. It might seem familiar to you. We've come across it before. And you can imagine that there's a question that's asking us to find the derivative of this thing. And I'm going to introduce to you the concept of log differentiation. So if you're going to try and take the derivative of this thing, there's a few problems. A power function So a power function requires a constant exponent. And we can see here that x is in the exponent, so this can't be a power function. And an exponential function requires a constant base, but we see x is in the base, or x, I should say, is the base. So it can't be an exponential function. And since the above is neither a power function or an exponential function, we can't use the power rule or the exponent rule to find the derivative. So that's the problem. That's the problem with this function. It's why it's sort of showing up in this course. Why it showed up earlier was so that we could get to this moment and I could teach you something about log differentiation. Because it's going to turn out that this function is, in some sense, it's a log function. And I'm going to show you how, with log differentiation, we can find the derivative. So let's use log differentiation to find the derivative. And that's exactly what we're going to do on the next slide. Now, before we jump into the math and algebra, I'm going to make a little note here. This is a preview of implicit differentiation. And that's topic or textbook chapter in section 7.1. So that's going to be one of the next topics that you're going to see in this course is going to be implicit differentiation. And this is a sneak peek of that. So let's take a look. So what do we mean by log differentiation? Well, I'm going to take the natural logarithm. I guess I'm not going to start writing log now. Take the natural logarithm of both sides of this expression. I know, it's kind of crazy, right? These two things are equal to each other. The left-hand side is an abstract function of x, and the right-hand side is explicitly written what the function looks like. But as long as I do the same procedure to both sides, I haven't broken any rules. So that's what I'm going to do. And when I take the log of x to the power of x, I'm going to get x log x. And you can kind of see that I should be able to take the derivative of the right-hand side. Right? It looks just like a product of two functions, one of them which happens to have the natural logarithm in it. And so I'm going to do just that. So I'm going to take d of x. I'm going to take the derivative of both sides. And what am I going to get over here? I'm going to get 1 over f of x. Right? That's just the basic, that's the derivative rule for logs. And I need to use the chain rule. because this thing is like writing g of f of x, right? So where g is the natural log, right? So I've got to use the chain rule here, which means the derivative of the inside in this case is going to be the derivative of f of x. So I've got f prime x over there. Now we move to the right-hand side. The right-hand side, I'll take the derivative of the right-hand side. So I'm going to get 1 times log x plus x over x. Now I'm going to clean up this right-hand side, but before I do that, let's take a look at the left-hand side. I know that this thing here is equal to this thing here. And so I'm going to replace the left-hand side like so. And over here I've got log x plus 1. And I want to move my x to the power of x to the right-hand side. So I'm going to multiply it, both sides, by x to the power of x. And I was able to find the derivative of this function by using log differentiation. And log differentiation is very, very handy. Comes in useful very often in economics, as you will see in chapter 7. Think elasticities. So think of elasticities. Maybe you saw them. Hopefully you've seen them in Econ 1010 or Econ 1000. And if you haven't seen them in Econ 1000, you should see them soon. Here are 2 practice problems. Why don't you press pause, give them a try, and then we can go through the solution together. All right, let's look at the first one. So we want to find g prime x, and that is equal to, well, I can make this a little bit easier on myself. So I've got a 4 here. I can bring the 2 down. So we've got 8 log x. I take the derivative of that, and what do I get? I'm going to get 8 over x. 8 over x. Now let's see what happened if we didn't do that. If we just left it on the level as it was, if I want to take the derivative of this, I'm going to get 4 over, everything that's in the log moves into the denominator. So we get x squared. But now we have to use the chain rule. So we have to use the chain rule. We have to take the derivative of all the stuff that is inside the natural logarithm. And so that's going to give us 2x. And then we've got 2 times 4, that's 8. X divided by x squared, that is 1 over x. So we've got 8 over x, and we've got the same answer either way. Looking at the next problem, we can see here that it's neither an exponential function or a power function, because both the exponent and the base are changing. So we're going to have to take the log of both sides of this thing. And if we do that, we'll get this thing. Now I want to differentiate this whole thing with respect to x, and I get 1 over f of x times f prime x, which is equal to -1 log x plus 1 over x times 2 minus x replace this thing with what it's actually equal to. We've got this very ugly looking expression that looks like that. Not a lot of simplifying we can do with this thing, but it seems to be the right way to take the derivative of this. Of course, we had to use the log differentiation technique that you learned about on the previous slide.